All right, next concept we're going to look at are electron dot diagrams. These are also called Lewis structures or Lewis dot diagrams, and they basically merge two concepts. They merge the idea of valence electrons and they merge the idea of orbital notation. And this is all going to come together in the next section on bonding. So really important that you have these foundations down first. So what you're going to be doing is we're going to look at this idea of sodium. So if we were doing the short form orbital notation for sodium, we would just have one arrow. So what that means on its dot diagram, it's going to have one dot. And it really doesn't matter where you put that dot. So all of these would be equivalent dot diagrams. Now you don't have to draw them all, but the key idea is that there is a single electron in sodium. So if you look at chlorine, we have its short form is going to be 3s with a pair, and then there's 3p orbitals, and we're going to have 1, 2, 3, 4, 5. So when we do chlorine's dot diagram, we're going to have these two paired, and I always fill them in the same way I do the arrows. So these are my S's, and then I'm going to do one on the P, one on this P, and one on this P, and then I'm going to pair them up. So what you should see are 3 pairs and a single, which is exactly what we have here, 3 pairs and a single. So the general order for any element X, and again, doesn't matter where you start, I just tend to always start on this right side. So my first electron, my S1 and S2 are going to go here. My P1 is going to go here, my P2 is going to go here, my P3. So again, if I'm numbering these, this is my S1, this is my S2, P1, P2, P3, and then this would be P4 and P5. Oops. P4, P5, and P6. So it basically mirrors the same orbital notation. If we want to look at it from just total valence electrons, so we wouldn't say, oh, we have 2s and 5p, we would just say 7. So this is from orbital notation, and this is going to be from valence electrons. So if I'm saying that there's 7, my first 2 go together as a pair, my third one's going to go here, my fourth one's going to go here, my fifth one here, sixth one down here, seventh one here, and eighth one here. And again, that is pairing the order of the S and the P. So 1, 2, 3, 4, 5. Again, so if you can think of each of these sides of the box as one of the orbitals. 6, 7, and 8. Okay, so another way of looking at this is the s orbital. This side here is the s. This side here is the px. This side here is the py, and this side here is the pz axis. So it's again kind of summarizing those three-dimensional space idea. Okay. The next one I think we did was chromium. So that was your 4s2, 3d4. So again, the D's aren't part of our valence electrons, so chromium's valence electrons would look like just a pair. So you want to be careful that you don't have them spaced out so far that you're not sure if it's, you know, is it 2 singles or is it a pair. So you want to make sure they're kind of nice and tight together. And I'm sorry, my erasable pen is not erasing as well as I'd like. So I want those nice and tight together so I can tell they're a pair and not 2 singles. Okay. When I go to tin, that was the last example we did, I have that 5s2, 4d10, 5p2. I am going to just have tin. Let me get rid of that stray mark there, hopefully. So I'm going to start with my 2 s's on this side, and then my 2 p's. I'm going to have 1 here and 1 here because it's orbital notation is going to look like this. Now I'm going to skip the D's in the interest of time. Okay, those would all be filled, but they don't show up here anyway. So that would be your electron dot diagram for tin. Now, I do have to tell you that your book does this differently, and the reason they do it differently is because of carbon. So you may remember carbon from biology, that it can make 4 bonds. So eventually these are all going to be bonding locations. So what happens with carbon? It has what's called a hybrid orbital. So it doesn't follow the rules. So your book decides to kind of model everything after what carbon does, because there are so many carbon compounds. I think you're smart enough to be able to handle one exception of carbon and follow the rules for the rest of them. So carbon is 2s2, okay, 2p2 is what we would expect. But what it does is it promotes this one from the S to the P. So if we would normally expect this for our carbon, it decides that dad shouldn't be in the room with mom and dad should have his own bedroom. So mom's kicking dad out so that no one has to share a room. So what it does is this. So again, I'm not going to ask you to know that exception, but you will have seen that exception as well. So when we do carbon's electron dot diagram, and I know you did these in biology, so hopefully a lot of this is review, carbon's electron dot diagram looks like this, but it's because it's an exception to the rule. So your book basically follows everything and puts 1 on each side before they pair up, and that's really true for carbon, but it's not true for most elements. So I'm going to ask you to follow the rules that I gave you. Okay, so I'm going to give you a practice sheet to work on, and I'd like you to fill those out and submit that.